In fact, the answer was yes. You said no, but the answer was yes. It's chemistry time. Today we are talking about stoichiometry, so please head your paper, stoichiometry, spelled S-T-O-I, at least it's spelled in English, S-T-O-I-C-H-O-M-E-T-R-Y, stoichiometry. I'm not at the board, as you might be able to tell, even you viewers online. Welcome, viewers online. I'm not at the board, as you will probably be able to tell. But if I were, what do you think I would write on the board? I would probably write stoichiometry. And then what do you think I would write after that? What symbol do you think I would draw underneath the word stoichiometry? If you had to guess. I do this a lot, is why I'm asking you. No, I mean eventually. Let's do this in brown, homie. Stoichiometry. I don't know if that's actually how I said this. What symbol feels right to go underneath this? Maybe you even have it in your notes. Sometimes I'm making fun of myself. This is a meta reference. Hey, is the mic picking up? Is that little bar on the bottom with the balls? Is on the bottom right of the monitor there? There should be. Okay, thank you. What symbol do I often draw underneath the word to indicate that we're going? What are we going to do with the word?
A line.
Break it down.
Break it down. We're going to break it down. Well, what line? What kind of, like, come on. You've seen me do this a million times. You just don't ever pay attention to me. This comes from the Greek word stoichios. Oh, there should be a omicron there. Stoichios and metros. Stoichios meaning, as you probably know, Greek scholars, element. And metros, you actually probably do know. What is the suffix meter in things like geometry or, I'm trying to think of another one, trigonometry. What's the meter mean? And it's also where we get the word meter from, the root word of meter. Measurement. Yeah, exactly. And this, in a nutshell, is stoichiometry. I mean, really, I could just say bye and we would be done, because that's what stoichiometry is measuring the elements, and not just elements, but substances. But instead, we're going to go into a little bit more detail, and part of what we're going to do is write down the objective, which is what? Let's see.
Stability and change in chemical reaction.
Calculate, is that the verb?
Compute.
Compute, ooh, very nice. Compute. Stability. And change in chemical reactions. We've done chemical reactions as kind of their own topic, and now we're going to be computing. What kind of thing does that imply if we're going to be computing?
Decipher.
In a sense, using what toolkit? Of the toolkits that you learn in school, which one are we going to be using if we're computing?
Moles.
Yeah, but you're being too specific. Broadly, what toolkit are you using? What subject material are you going to be using if you're computing?
Science mention.
Not wrong. No. What toolkit
SI.
that you learn in school from the time you were very young?
Unit conversion.
From the time you were very, yes, okay. Now you're not being broad enough. Numbers, what do we call it when we compute with numbers? Math. Yes, we're doing the math of measuring the elements. Really, really basically, what we're doing is converting from an amount of one element, not necessarily a chemical element, of one substance in a chemical reaction, to another. And the measurement part of that, the computing part of that, is the numbers that we use, that we are now applying numerical, computational, conceptual framework to our chemical reactions. So we might have, I don't have it, of course, because I've erased the whiteboard since then, but what is the example we use for a chemical reaction? One of the examples we use from your notes of a chemical reaction.
Photosynthesis.
Okay, let's do the photosynthesis one. Which is, you tell me, what is photosynthesis? What's the chemical reaction for photosynthesis? Let's do it in green. Go on. You were going to say. Okay, let's not start with that because that's a product. What are the reactants?
Cellular respiration.
What are the reactants in photosynthesis?
CO2 plus H2O.
CO2 plus H2O yields C6H12O6, glucose sugar, plus oxygen gas. And this only happens in the presence of light. Okay, photosynthesis. A chemical reaction. This isn't a reaction. This relates to the part of our objectives where we are talking about chemical reactions. And now we're going to compute the stability and change in it. So I chose stability and change because that's one of the cross-cutting concepts. But we're going to be talking about how the stability is that these specific chemical elements, I'm using the word elements in kind of two different ways. I do right now mean specific chemical elements, carbon, stays, stability, stays carbon. It's still carbon before and after, right? The oxygen is still oxygen before and after. The hydrogen is still hydrogen before and after, right? But they change. They change what they're bonded with. In this case, it's just carbon bonded with 2 oxygens. And in this case, it's 6 carbons bonded with 12 oxygens and 6 oxygens. Sorry, 12 hydrogens and 6 oxygens. Stability and change. Yeah? The essence of stability in this is called, I'm going to give you a sentence frame, the law of what? What governs the stability of this, the things that stay the same? The law of conservation of what? Mass. Which BT dub is the same as the law of conservation of energy. Those are two sides of one coin, but we in chemistry specifically refer to the law of conservation of mass. So that tells us that something has to stay the same. The elements have to be the same on one side of this yield sign as the other. We can't have carbon on this side and no carbon on this side. That wouldn't have satisfied the law of conservation of mass. But there was also change. There was stability in the types of elements, but there was change in what they're bonded with. There was stability even in how much of them there are. How do we indicate that in a chemical reaction? That was chapter 9. What do we do to indicate? Yeah, we balance it. So let's balance it. You take a second to analyze this and tell me what I should write. What element should we start with? What chemical element should we start with? That's not an element.
Carbon.
Let's start with carbon. I prefer to start with not hydrogen and oxygen. So let's start with carbon. How can we balance carbon on either side of the yield sign?
6 on the reactant.
Let's put a 6 in front of the reactant. Remember, we can only adjust the coefficients. This should be a review. This is one of the main things you'll be doing this chapter. The things that I'm worried about that you won't be able to do is balance, something that should be review, and naming and writing formulas, something that should be review, including polyatomic ions, something that should be review. Those are what I'm worried about. The thing that we're doing that's new that we'll get to in a second, I think you'll probably get it pretty easily. So let's continue balancing. 6 carbons, now what?
Hydrogen.
Let's do the hydrogens next. Let's put a 6 here and see how that suits us. So 6 hydrogens, that makes it 12 hydrogens. And now we have how many oxygens altogether? Well, we have 6 times 2 is 12, plus 6 is 18, and over here we have only 6. So we need to make this one into 12. So yeah, we'll put a 6 there. That's balanced. So now that's a balanced chemical equation. So step 1, if you're writing steps, I sometimes write the steps, I'm not going to this time, but if you want to write steps down, step 1 is balance the chemical equation. Step 1 is balance the chemical equation. That's the first step of measuring the elements. So the first step of stoichiometry is to balance the chemical equation. Now where the computation comes in, you could say that that's math, but that's, I mean, if it's math at all, it's like 3rd grade math. The worst math we did was multiply 6 times 2. Where the computation comes in is that you might be told, as part of your given, you might be told 18 grams of CO2 is absorbed by a photosynthesizing cell. Compute the amount of sugar it can produce in an excess of oxygen. That might be a problem we're given. This is a stoichiometry problem. Balancing the chemical equation is not a stoichiometry problem. But this is a stoichiometry problem. So we're told that we have 18 grams of carbon dioxide. I even use this word compute to relate to our objective. And we're told that we want to find how much, right, compute the amount of sugar it can produce. So what can we do first? Well, we balance the chemical equation first, and then we start with our given, the given amount, the given metros. 18 grams of CO2. You should be writing this part down. So step 2 is write the given. What does step 2, write the given, sound like? What kind of math does that sound like when we maybe? But I was thinking of unit conversions. If you rewind your mind, or if you're watching on YouTube, you go back to the August videos. Write the given was the first step of the unit conversion. And fundamentally, the math, the computation that we're doing here is the unit conversion. So we're going to convert from 18 grams of CO2 to moles of CO2. And I want you to stick with labeling. I told you this in chapter 10, I think even on the video. Label your units. I mean, like, unit your units. So you have grams, but you need to be more specific, grams of CO2. You have moles, but you need to be more specific, moles of CO2. And here's another trick, not necessarily the rule, but the trick is put all your units in first. This is just like unit conversions, and then put in their numbers. So what then will we do? Well, we don't want to be talking about moles of CO2. We want to be talking about how much the amount of sugar. So we're going to convert from moles of CO2 eventually to moles of sugar, C6H12O6. Label them both. Now I hope this should be very clear to you why I want you to label your units. Because if you just had moles here, moles to moles, well, that could be anything. But moles of CO2 to moles of C6H12O6, that's a different thing. Those are different things from each other. And then we're talking about compute the amount of, I should have probably put mass of, moles of C6H12O6. We're going to convert that back to grams of C6H12O6. Now watch as I put the numbers in, because we need to do some side math to do it. How do I know, how can I convert how many grams are in 1 mole of CO2? How do I find that value? This is from chapter 10. This is now chapter 11, but we did this in chapter 10. How do I find the mass of 1 mole of CO2?
You look at the periodic. You find the atomic weight of carbon
Yep.
and oxygen.
Yep, I have to do carbon and oxygen. Is this still showing up on screen? Can you see if as I'm writing over here, it still shows up?
Yes.
We have to add them together. Carbon is 12.011 grams per mole. Oxygen is 15.999 grams per mole. Someone get a calculator out. We have 2 of those. We're going to multiply them by 2. 16 times 2 is 32, plus 12 is 44. I'm going to put about 44 grams per mole. So we have, in 1 mole of CO2, 44 grams of CO2. You with me so far? You see where I got that value from? Well, and this, do I have to show this when I do my work? Yep. Every problem you do this for, you have to show this. Now, this is the most important part. This is actually fundamentally the only new thing in this whole chapter is this. I'm going to do it in red. How do I find how many moles of CO2 is equal to how many moles of C6H12O6? I'll give you a hint. It was from step 1. Where do you think I get numbers for these lines? From step 1.
You take C, H, and O, and then times it by C by 6.
Nope, I think you're thinking of what we'll do here to get how many grams 1 mole of C6H12O6 weighs, or the mass of that. But how do I find how many moles can convert to, I want to convert from moles of CO2, a certain substance, to moles of C6H12O6, a different substance. What numbers will I use there? The answer is the coefficients from my balanced chemical equation. What's this coefficient? I underlined nothing. What is that coefficient? 1. It's not 0, it's 1. If we don't have a coefficient, it's 1. And what about CO2? Well, that comes from over here. So it's a 6. Just the coefficients from the balanced chemical equation. I made this up, but I love it. This is the heart of stoichiometry. Please put a heart around that. I like this for 2 reasons. 1, I think it's cute. 2, Every single stoichiometry problem will have this. If you put a heart around this part of it, you will know you've done it right. If you put a heart in there, you've done it right. If you haven't put a heart, you've done it wrong. You always have this. This heart is called the mole ratio. The ratio of one substance to another as measured in moles within a balanced chemical equation is called the mole ratio. Also, it's almost Valentine's Day, and so if you want to impress the honeys, that's a gender neutral term. If you want to impress the gender neutral honeys, sweetheart, write them a Valentine about stoichiometry. It's got the heart in it, the heart of the mole ratio. The stoichiometry cannot live without a heart, which is the mole ratio. Every stoichiometry problem will have this. If you start writing a heart around the mole ratio, how will I know it's the mole ratio? How will I know to put a heart around it? I'm converting moles to moles. That's what it is. Moles of one thing to moles to another thing. That's the definition of stoichiometry. This is how we measure the elements, is convert moles of A to moles of B. That's what makes it a stoichiometry problem. We're converting from one thing to another thing. Back to our math, we need to show this. How will I find how many grams are in 1 mole of C6H12O6? Again, back over to here, the side note box, C6H12O6, C 12.011 grams per mole. There are 6, H 1.0079 grams per mole. There are 12, and O 15.999 grams per mole. There are 6. So C6, H12, O6. Now I'd like your calculation help with this one, please. I can probably do it in my head. 6 times 12 is 72, and 12 is 84, and 6 times 16 is 96, and whatever I just said, 84 is 176. Is that right? Faster than calculator. Might be wronger than the calculator, but I was faster. Excuse me.
I got 179.994.
Okay. 180. I don't know if I was right or not. Someone on the YouTube comments can... I did re-enable comments from my video, so if you want to leave a comment, shouldn't have probably told everyone that. Anyway, now we just do it as a conversion. In our calculator, we type in 18, divide it by 44, press enter, divide it by 6. Why am I skipping these top ones? They're just ones. They don't change the value mathematically. If you have to think about it, fine. But let me start over. Now, 18 grams divided by 44, enter, divided by 6, enter, times 180, enter. And what is my unit going to be? Well, before we write down the math, let's look at our units. Grams of CO2 reduce out, moles of CO2 reduce out, moles of C6H12O6 reduce out. We're left with grams of C6H12O6. And that value in grams is what?
12.27 repeating.
12.28 grams of C6H12O6. Now you ask yourself to check for reasonability. If I had 18 grams of carbon dioxide used, would it make sense for 12 grams of sugar to be produced? Sure, I can't think of a reason why that wouldn't be. Right? If you end up getting 7.9 times 10 to the 17th, probably wrong. But this is within a realm of reasonability, I would say. That's stoichiometry. Literally the only new thing. You knew unit conversions. You know how to add up the molar mass of substances. When I say you know how, I should be saying you should know how to if you followed along in previous lessons. You know how to do unit conversions. You know how to add up molar masses. You know how to balance chemical equations. The only new thing is using this mole ratio to get from moles of one thing to moles of another. Now, there are intricacies of this that your book goes into, finding limiting and excess reagents. I actually have videos about that. Computing percent yield, I have videos about that. Computing error in percent yield, I have videos about that. But this is the essence of it, and it's one new thing, the heart, the mole ratio. Do you have questions about that one new thing? You have questions about any of this?